Hey everyone, welcome back for Lab 5. This is your last lab. And today we're going to do something extra fun. So bear with me for the next 20 minutes or so and we'll get through this and we'll get to the fun part. So it first asks us to connect the circuit as shown in figure 5. So if you see on my screen here, figure 5 is the drain and the gate actually connected. It's a diode connected MOSFET in this configuration. And then you always consequently have saturation mode by allowing that VDS is always greater than VGS minus VT. So the second step asks us to adjust VDD so that its name as a variable you recognize, and run a DC sweep using this variable. Sweep it from 2.1 to 3 volts in linear steps of 0.1 volts. So there's a lot said there. I'm going to unpack it for you. Let's go over to Multisim and check it out. So basically the first thing is it wants us to adjust this VDD and name the source something that we recognize. So it's already named as VGS for you. You don't have to go and switch it, but just in case you wanted to name it something else, you could. So that's where the actual naming convention's done. Go ahead. And then you're going to go into your actual sweep menu up here. So at the top, you'll see an interactive button. Go ahead and click on that, and that'll let you pick between DC operating point, DC sweep, AC transient, and all the different kinds of sweeps. So basically, what I'm going to want you to do for the first one, 5.1, is sweep VGS, which is this source down here, from 2.1 to 3 volts in increments of 0.01 volts. Okay? It's that simple. So go ahead, click on save. And now you'll see that there's a DC sweep set up here. Make sure this value is a 1 kilo ohm resistor, and then you're going to go ahead and actually run the simulation. Once you go ahead and run the simulation, you should have a graph, something like mine, that pops up. Once you have that, you can go ahead and click Tools and export the file to Excel. So go ahead and export to Excel, click OK, click OK again. So now we've adjusted VDD so that its name is a variable you recognize. We've ran a DC sweep using this variable, and we've swept it from 2.1 to 3 volts in linear steps of 0.1 volts. So next, we tabulated the results using Multisim Tools Export to Excel, and then check the trace of interest. Okay, a new window will appear. And then we're going to rename the columns. So let's go into our sheet here, and our X trace, we know what that is. It's VGS. Our Y trace is actually VD. Okay. So if we wanted to calculate ID, how would we do that? We would go down here. We would type in a new formula, right? And we would type in VGS minus VD, all divided by 1 kilo ohm will give us our current through that branch. So if we go ahead and have that formula for the first cell, we can go ahead and drag it down using this button here to drag it down for all the cells. Now once we have the current through each branch, we need to find the square root of ID, as it asks us to do. So go back to our table, click on OK, type in an equal sign again, square root, search for the square root. You'll be able to find a square root of a number. So click on C2 and then close off the bracket and hit enter. And then drag that one down, just as we did last time. So now we can make both plots. We can make VGS versus ID and VGS versus the square root of ID. So let's go ahead and first we'll measure VGS versus ID. We'll insert that plot. And we can see that the device is clearly not in saturation until it gets to around 2.2 volts or so. So in our next curve, where we're actually mapping VGS versus root IDS, we only want this linear region, okay? We only want this region where the device is in active mode. So let's just go from this corner here, which is around 2.24, up until the last digit. So let's find 2.24. This could be different for you guys, so just make sure you're looking at it while you're doing it. And drag down as you're matching the columns. So go insert a new chart, and you can go ahead and name that chart. But before you do that, make sure you're adding a trend line, linear trend line, and then if you click on the actual trend line itself, it'll let you display the equation on the chart. So once you have a rough estimate now for the linear region here, you can go ahead and calculate the square root, 2 times the slope squared, which will give you an estimate for the K value of this particular MOSFET. So in my case, I got 0.0285, and then I'm going to multiply that by, I'm going to square that, I'm going to multiply that by 2, then I'm going to multiply that by 10 to the 3 to get it in milliamps. So I can see mine is approximately 1.6 milliamps per volt squared. If you weren't too sure what I was doing there, I'm doing something just like this. So go to some random cell, type in your slope, square it, and multiply it by 2, and you'll find a value. If you multiply that value by 10 to the 3, you should be in milliamps per volt squared. Make sure you're labeling this chart, and make sure you're adding axes or labels to your axes as well. So it also wants us to identify this VT value, right? And as I was just talking about, the VT value is roughly 2.24 in my case. So I want you guys to go actually look at the data sheet for this particular device. So go look up the 7000G. I've attached this link in the actual lab manual, but if you can't find it, you can just go search it on Google, go to the first product page, and bring up the data sheet. And from there, you'll be able to find an estimate for the actual threshold voltage to turn this device on. And that'll be in this table here. So the typical value, the minimum, and the maximum value. Typical value is around 2.1. So let's see, again, go back to our Excel table. 2.24 is what we had. 2.1 is roughly there. So you're going to compare it to the data sheet and notice why it may be off, why it could be the same. Notice these characteristics that are defining the typical gate threshold voltage. So just something to take note of while you're running your lab. Being able to read a data sheet is an extremely important skill too that a lot of people even in 4th year don't have. So if you guys understand how to read data sheets, you'll be way ahead of some of your peers. It also may be apparent to you now why we got you to run the linear sweep from 2.1 to 3 volts in steps of 0.01 volts, because the typical gate threshold voltage is around 2.1. So make sure, obviously, you've recreated this kind of table in Excel so you can attach it with your report, as I have here shown you. Then you've created this graph, you've measured the best straight line using Excel, and yeah, you don't need to worry about the graph paper at all. So next step is designing the Enhancement NMOS-based audio amplifier. So here's where we're actually going to get into some of the fun stuff. We're first going to measure all the characteristics of this amplifier that we've designed, and then we're going to actually measure some audio on it. So in a normal lab setting, you would have to recalculate all these values using the new K and VT of your device, but in this case, we don't have to do that. So go ahead and actually connect the audio amplifier Make sure you have R1, R2, RS, and RD calculated, and then plug them in. So I actually already have my audio amplifier made. I've used a little bit different values than what you guys are going to have. I've used a 90k ohm load and a 9k RD. Just to differentiate my work from what you guys are going to do. So let's show you actually what I first calculated. What I first calculated here was 65k. So 65k. Oh, not 65 ohms. 65k ohms. Okay, and we'll see that the operating point is a little bit off from where I want it to be. So we'll go back actually, before I do anything, let's check the actual sweep that we're on. So currently we're on a DC sweep. I want to go back to the interactive simulation and hit save. Once I've done that, we're all set, we're all good to go. So go ahead and hit run. Now we're running. And now we can actually place this voltage probe on the output, or sorry, on the drain, and see that my VDC isn't close to VDQ. Well, it's somewhat close, but it's not as close as it could be. So now, this is when you actually adjust R2 to get it a little bit closer to VDQ. So I adjusted to 59k, and I ended up with a VDQ of around 7.47, which is very close to 7.5, which is nearly half my supply, which is exactly what we're looking for. So the next portion is asking us to actually measure the DC operating point. So if we go ahead back into our interactive simulation, click on that button, we can go ahead and find the DC operating point as well, okay? And from there we can select the variables of interest that we're interested in. So we're going to go to circuit voltages, and we're going to see what the nodes are labeled. So we can see the gate is labeled node 2. So we want to make sure we're going to plot, well actually, first, before we do anything, let's make sure there's no variables that are currently being plotted. So let's remove everything, then go ahead and add the variables of interest. So at our gate is called V2. So let's make sure we add V2. At our drain, at our source is called V1. Let's go ahead and add V1. And then at the actual drain here, we have V3. So let's go ahead and add V3. So once we've added all three of those variables, we can hit save, and we can hit run again. So this will pop up a list with the actual voltages at each node. Once we have the voltages at each node, and we know the supply voltage, and we know these nodes are grounded, we can also calculate all the currents through each of the branches, and that'll give us our DC operating point. So if you want to take a screenshot of that for your report, you can. If you wanted to go ahead and add some more values to your DC operating point, you could also do that. So if we wanted to go add our circuit currents, so we could add I of V1, we could add I of V2. Sorry, make sure you're clicking on all variables down here when you're going to add the currents. So if you're going to add the currents, we need to measure the current through each one of these branches, right? So if we want the current through R2, we need IR2. IR2 we can add, IR4 we could add, IR3 we could add, and last but not least, we need to add IR5. So once we have those all added, we can hit save, we can run it again, and now we can see we have actually all the currents through each resistor and the voltages at each node. So that's your full DC operating point. You can go ahead and screenshot that if you want, include that in your report. Third step's asking us to connect the function generator, which is already connected for us. Well, not in your case, but you should have already connected it when you're running your circuit. Connect the baud plot functionality. So let's go back to Multisim. When you originally get these files, you're going to actually have no connections here. And that's just because we don't want you running your speakers and your microphone at the same time as you're running your baud plots. This makes the simulations extremely long, and you'll be there for a week. So basically, I'll leave these disconnected when you first get them, and you're going to have to connect V out like that, and V in like that to the baud plot and to the oscilloscope for the first portion, so 5.2. So once everything's kind of set up and you know your DC operating point's good, I'll run it once more just to show you. DC operating point's good, 7.445 at the train. Then I'll go back and hit DC operating point once more and go back to the interactive simulation. Hit save and go ahead and run it once more. So now we should be able to get an output in our baud plot. And you'll see sometimes these scales will be off, so you gotta adjust them to actually get a nice waveform and actually start your initial value at 50 or 100 hertz. Doesn't matter. You can go up to 1 gigahertz, but make sure you're not including all the transients that are before 50 hertz. So make sure you're starting your initial horizontal value at around 50 hertz. Alright, so once that's done, you can go ahead and measure the passband gain, right? So I'll go around to my passband, and I can see that I have around 15 dB of gain throughout the whole passband. And then I can see that, so 15.72, so my 3 dB bandwidth should be around 12.72 dBs. And I can see my cutoff is around 1.5 megahertz. So make sure you're tabulating these values as well, because I'm going to get you to plot them the same way you did in lab 4 with the hardware, along with the hardware portion of the lab, and actually notice the differences and the similarities between the two baud plots. So go ahead, take about 20 points of interest along this graph. Take more at the quarter frequencies where it actually moves here. So you can, on these linear portions, you can take a lot less, but where the curve starts to happen, make sure you take a lot more points. Okay, now that you've taken a screenshot of your baud plot, I'd imagine you've taken the 20 points of interest from around 1 kilohertz to, I'd say, 10 megahertz, I believe. So take about 20 points in between there, and yeah, you should be good. So now, slowly increase the amplitude of the input signal until you see some distortion. So measure the voltage gain and sketch the distorted waveform. So the voltage gain will be the same. We won't do this again. I'll actually omit that while we're talking here. And then we're going to actually just sketch the distorted waveform. So not sketch it. We're going to take a screenshot once again. Go ahead, hit run. Hit, let's try 1.1 volts to begin. Okay. Make sure your oscilloscope is also connected. You're going to have to lower the channel B down. You might want to zero channel A. That's fine. We're not really worried about the input voltage, so zeroing channel A is fine. Channel B, we can see, is clipping, right, at 1.1 volts of input. It's clipping on the bottom because we have these, they're non-apparent peaks. That's probably not the starting. So move your markers into place, get the output versus the input, so we can see we have 11.16 volts over 0.95 volts peak. So multiply this by 2 and divide this by this, and you'll have the voltage gain. Yeah, so first I said don't measure the gain, and then I actually measured the gain. So I would suggest you measure the gain, just because there is going to be some difference, because this waveform is clipped on the bottom, as you can see. So yeah, make sure you're actually remeasuring the gain on the oscilloscope, and then actually screenshotting the distorted waveform. So once both those things are done, we can move along to part 5. So basically, right now, the peaks and valleys of the output signal aren't clipping at the same time. And how would we make this happen? I want you to comment on that in your lab report. Think about something between the swing point between here and here. So whatever the voltage is on the actual source, and whatever the supply voltage is. So think about how this point is kind of centered in between VDD, but it doesn't really go down as far as it could, right? Because if we were to actually swing down to 0 volts would be ideal here. So make sure you're commenting on that in your lab report, and then we'll move on to part 6. So part 6 says to connect a 10 microfarad capacitor. Actually, I have to switch that while we're here. I only have 100 microfarad. That's fine. It won't make a difference. And then we're going to connect it in parallel with RS, and we're going to observe the polarity rule. So make sure you know that the positive terminal of the capacitor is here, and it needs to get connected to 1, because that's at the higher potential than 0, right? So once that capacitor is in place, go ahead and stop the simulation, rerun, and open up the build plot, and you'll see that your gain is completely off the screen now, because it's getting so much gain in this circuit. So now if we go through the passband, maybe switch this to around 100 Hertz, just to get a cleaner passband, we can see that our gain in the circuit is around 40 dB per decade in the passband. That's an incredible amount of gain. And we can see that our 3 dB bandwidth is actually decreased, right? So 40.5, we should be around 37.5, which puts our 3 dB bandwidth around 590.707K. So we have this steep decrease in bandwidth for the circuit, but we also have a large increase in gain. So there's clearly some trade-offs to putting this, bypassing this source resistor here, right? I want you to explain what those reasons are and note them in your lab report, and yeah. Then we'll move on to the very last step of the lab. And this is the fun part. So it asks us to delete V2, the sinusoidal input to the gate of Q2. So let's go back here. We can close both our scope and our build plot, and we can actually delete V2 from the circuit. Okay, the circuit's fine like that. Then we're going to actually delete our V out and V in from both the build plot and the oscilloscope. This is just going to help our simulation run a little bit faster. So next step, there's 2 remote settings that I get you set up. So go to remote desktop, go to the remote desktop app itself, okay? And you're going to go to local resources and click on settings and say play on this computer and record from this computer. Hit OK. If this isn't the usual way that you connect to your remote desktop, I'm going to get you to do it for this time. So make sure you're logging in to going to remote stats, and then actually finding your computer's number here. So the IP address is beside the computer name, and if you type that number directly into the remote desktop connection while you're connected to the VPN, like you see here, then you should have those local resources that we just talked about enabled. So make sure you're heading to General, Local Resources, Settings at the very top, Remote Audio Playback, play on this computer, and Remote Audio Recording, record from this computer. Click OK, and click Connect. So once you've done that, you should get a prompt 2 for your password. And now you're logged in. The third step I'm going to get you to do is download Audacity from this link onto your computer. It's available for OS X and Windows. You're going to be able to record your voice in Multisim in this portion of the lab. So go ahead and download that piece of software, and yeah, we'll get started. So now is where we'll be using these two things at the bottom of your actual sheet here. So the output and the input. So we're going to go ahead and actually wire those out. So go ahead and wire V out into the input of the speaker, and wire V in into the output of the microphone. So on the remote desktop, your circuit is going to look like this somewhat. And then you're going to double click on your speaker, and you're going to double click on your microphone, and they should both now say remote audio. So now you can switch the recording duration and the playback duration to whatever you so desire. Leave the sample rate at 11.025 on both the speaker and the microphone to allow you to actually play the sound. So on my system, they just look a little different for me because I have Multisim installed locally. So I'm actually going to play it through my speakers in my home, and then I'm going to input it through my microphone in my computer. So let's go ahead and find a good tune to play. Alright, this sounds like it for me. So I'm going to hit record. Should record the audio. So now that that audio is recorded, I can go ahead, and now that my simulation is still on interactive, just go ahead and hit run, or hit run here, doesn't matter. Now you're going to have to wait quite a little bit until this transient down on the bottom right, see where my mouse is, gets to 10 seconds. Once that transient analysis gets to 10 seconds, you can hit stop, and then you should be able to play the sound back. So while we're waiting, in your case, it's going to be recording from whatever your default device is in Windows or Mac OS, because it's recording from your computer. So this remote audio on both the speaker and microphone indicates that it's recording from your computer. So again, whatever your default input device and whatever your default output device are, that's where the audio will be playing from. Okay, just make sure you remember that. So as you can see, I've already been here for probably 30 seconds, and I'm only at about 3.5 seconds of my transient simulation. So just be patient, and that'll eventually get to 10 seconds, I promise. Oh, sorry. Before I forget, guys, make sure you remove this bypass capacitor before you run this amplifier. Because as we've seen in the last step, with 40 dBs of gain, we're never going to be able to hear our voice. Our voice is always going to be clipping. So let's make sure we remove that bypass capacitor before we actually run the transient simulation. Now we'll go ahead and run it once more. So now that that bypass capacitor is removed, I'm still waiting the 10 seconds, so just bear with me and it'll be done soon enough. Yeah, so all in all, you're probably going to have to wait about 5 minutes to process 10 seconds of transient audio. So once that transient simulation reaches 10 seconds, like I said, hit stop, and then you should be able to play the sound. So now that the transient analysis is done, head back to your actual speaker device, and you should be able to play that sound. As long as the repeat recorded sound is checked, you should be able to continuously play that sound. So I'll show you the amplified version of the sound that we just recorded using that song. You can hear it's a little bit distorted, and you can even also hear my voice in there when I'm talking to you guys in the middle of the video. But you can tell there's clearly an amplification of that sound, right? From input to output. As the recorded sound sounded something like this. Which was not nearly as loud as that amplified version. If we go ahead and play it once more. I'm sorry for probably blasting some of your ears out, but I was just trying to show a point there. So now that you've clearly shown that the amplifier works to actually amplify your voice or amplify sound, you can notice what is the distortion caused by. So there's some concepts that we went through in this lab, ideally or mostly figure 4 and figure 5, or question 4 and question 5 from 5.2, that kind of explain what the distortion is caused by. So you can explain that in your lab. And then last but not least, I'm going to get you to open a program like Audacity. So go ahead and open up Audacity if you're on Windows, and if you're on Mac, I have another sort of tutorial for you so you can record your sound. Yeah, so go ahead and actually open up Windows, and whatever you were hearing that audio on is the device that you pick. So if I was hearing it on my headphones, I would pick my headphones. If I was hearing it on my USB audio device, I would pick my USB audio device. Whatever you are currently hearing that audio playback on is the channel that you want to record. So first, your default will probably be MME, change to Windows Wasapi, and then change to the loopback of whatever device you want to record. So once you've done that, go ahead and you can actually go back to Multisim and open up this at the same time. And the shortcut to recording is actually just hitting the R key. So if we want to hit play sound and then go quickly back here and hit R. That didn't work very well. So I'm going to go play sound. Oh, didn't like that. Play sound. So now whatever's been recorded is just what's come through your headphones at that very moment. Because there was nothing coming through the headphones before, that's why it wasn't recording. As soon as it senses audio feedback, it can actually get it. And then we can actually clip this and trim this, get rid of that portion of the sound if we wanted. And then we could go File, Export. Export as MP3 or WAV, doesn't matter. I'll name mine Lab 5 Amplified Audio.mp3. If you go ahead and save that there, you can add your artistry name, your track title, your album number. You can add all those tags if you wanted, if you were to import it into iTunes for your awesome audio track. And then once that's all done, you should find an MP3 file created that has the tag that we just created. So after all those long steps, you've found some audio that you liked, you've ran it through an amplifier that you created and that you characterized in the previous steps, and then you put an audio input into that amplifier, you've amplified it, and you've recorded the output sound, which is, I think, a pretty cool little feat for this lab. So I hope that was interesting for you guys, and I hope you didn't find it too tedious. Anyways, have a good one, and we'll talk to you guys soon. Bye-bye. Oh, one more thing before I forget. Yeah, even if you're working on the remote computer with the remote audio, make sure you're actually doing the recording on your personal computer. So using Audacity on your personal computer, because you won't be able to download anything to the remote computers. So with that being said, that's everything. Have a good one, guys. Bye.